So deep learning is an area of research in machine learning, and this is a new name for neural network, in particular artificial neural network. And since late 90s, when first arose, neural network improved in algorithm methodology and was followed by other techniques such as support vector machines, boosting random forests, and then finally become deep learning. The structure of the model calculation is widely used for image, video classification, speech, and text modeling recognition. So this deep learning, it's basically neural network, but it's artificial neural network. So basically it's the reproduction of neural connection as neural network in biotechnology does. But there is a bit more like around algorithmics and predictions. So let's say that we do some example and say that we can have, for example, to start a single layer neural network, which means that we have so it's the basic of the basic model for deep learning. And we start with some predictors. Let's say we have p predictors, and as when we do modeling in general, we have a function. This function is basically our model and replicates the connection within the predictor to with some patterns to replicate the response. Okay, so the difference with deep learning is that we have a function of the predictors. So we do not just have an additive models adding like some predictors, just as the same as GAN models, for example, general additive models. Here we have a function of the predictors. This function that we it's this HK X function is the expression of the hidden layers. And for hidden layers, we mean an underneath pattern of the function that we establish, we set, we choose a priori which pattern, which hidden pattern we like to use, and following some criteria because of our data and for our final objective of our investigation. And then, so this goes in this within the structure of deep learning as an hidden layer. It's there's a name for this HK function, which is AK, because it's means activation. So it is an activation function with K activation parameters. So we can say that AK equals to HK of X. And again, we can assign this activation function to a special function G of Z, which is our function, our hidden function that we set as a fixed one that we chose. So this seems like a bit redundant. So like why we are setting all these things that if they are all the same thing. Actually, they are not the same thing because they can change. So you can set this as a specific function, and then you can have this with a slight remodification of this, and then all of these things is called activation function. The G of Z is this function here. So will be the bit that goes in our function model here, where is the HK of X is. So here that it's a model inside a model. So basically here we have the intercept, and this one are the coefficients for the hidden layers model. So to obtain an output layer, which is a linear model, for example, that uses activation functions as an input and resulting in a function fx, which is the one that we are aiming to achieve. So we can rewrite these things here as a ftx beta 0 plus the summation of this these two, setting the activation function. So we have these k betas, and we have these kp coefficients of the activation function itself, which are those things here. So let's see what are the options for the GZ function. These activation functions, which we set, there is a bit of like redundancy in saying those things, because it's always an activation function, but we start setting the G, which is always this one here, but this can change. So you know that this G of Z belongs to a family of functions that you can use as an underneath layer in the structure of your artificial neural network. And they can be a sigmoid or a ReLU function, a rectified linear unit function. Sigmoid, we know what is it, is this one here. And the ReLU function, the rectified linear unit, it's like an identity function. So it's 0 if Z is less than 0 and 1 otherwise. So you can imagine that we can say that our model, if our selector parameter is less than 0, will be always 0. Otherwise, will be equals to 1. So that means that would be more clear.
It should be it's Z when it's greater than 0, not 1. That's a typo. It should be
okay.
Z or Z. So that's why it goes up to the right. Yep.
Yeah. Okay. Yes. Okay, so this is a so the structure of. In fact, I was saying it is 1, and yes, it's Z. That's why it's this
right
this way. Yeah. Okay, this is the structure of a single layer neural network, and it's this one here. So you have your predictors, and then the hidden layers, and then finally the output layer to that replicates the response variable. So the predictors basically get with some coefficients and some intercept pass through the hidden layer and release some other coefficients, then that will be building up the final function. So in this example, we see deep learning applied to this example here, to dosage efficacy study, and the model parameter with activation function in the middle. This example here. So the parameters can be retrieved. So we suppose to understand the patterns that deep learning does, we hypothesize that we know the value of the parameters. Okay, so we assign some values to X and then do the maths that pass through this function that releases new values that will be building up our final function. Okay, the function that of our final model. So the parameters can be retrieved with back propagation, which optimizes weights for the coefficients and biases for the intercept. We will see about that later. For now, we're supposed to know what is the value of these parameters, and we investigate the calculation of deep learning model. So this is the function that we, the final value, so the function that we want to build. We have our beta, and then we have the activation function. So this G of Z is this function here. For in this example is the soft function, but then you can have a sigmoid or ReLU function. And this is the intercept, and these are the coefficients of our hidden layers. Okay, I found this in a nice, I don't know if I can show you this up. Okay. Video, neural network inside. So I don't know if I can do this without the sound, but what it does, it's basically explaining you what's happened inside. Oops. So, which will be the structure at the end of the green bell that we want to achieve. So this is to give you an idea of what's happening with deep learning. Obviously, this is automated. So when you set the basic of the structure, then you can modify it, adding more layers, or to this layer other parameters. You can do convolutions, you can do many things you think that would be suitable for your investigation. Going back to the book, the things that we have seen with the maths, so the summation of the coefficients and the intercept, is even in the book as an example. Now we can see the book and it's a bit more understandable. For example, here in page 406, you can see all the passages for calculating the estimated effects, supposing that we know the value of the parameters. So, for example, if we have two predictors, we have two hidden units, and we set our activation function to be z squared. So we start with these parameters, beta 0, beta 1, beta 2, and the other coefficients. This way we set our h functions, which is squared. Here is clear. Basically, you have this z squared. Z is all this bit here. As you can see, h is different from g of z. because H is squared. Okay, H has his structure, which is the summation of something, but it is squared. So this Z here means whatever is the structure of H, and the squared is that H is will take the structure of G of Z. I don't know if it's that clear in any ways. Is that in any manner clear? I don't know. But so basically it's like a matryoshka, something inside something else. So you establish the structure outside, and then if you say that that things will be squared, all that you establish inside would be squared. Any questions? So if we go back here, so we said that H is this function, hk of x equals to g of z. If we establish that g of z is z squared, this function here will be squared. If we say, I don't know, like the log of z, this h function would be the log. So that is the reason for which those things are equals, but at the same time different. Because they can change anytime. So are equal, but are different. So here you see that this is squared. Okay, so what we want is to build our function. So we sum beta 0, and then beta 1, and then the h1, and so on and so forth. So we obtain as a result x1 times x2, which is our function. Okay. So the bit which is interesting is this is not the end of the story, because now, as any other models, we want to reduce the error. Okay, so we have made this bell curve, but this bell curve is most probably far away from the real values, because there is like a shift within the value that we have hypothesized to the value that are the most closest one to our observations, and so for new data, in case of new data. So what we need to do, as always when we do modeling, is to minimize the residuals. So if we do a quantitative neural network, we do minimize, as we know, the difference between observed data and predicted data squared. So if we do qualitative data, here is the case of cross entropy. So I've already mentioned this, and this will be explained more clearly in the multi-layer neural network section. But this will be the case when we use the log of the function, and this summation will be the minimum value that we need for minimizing the errors. Okay, so for some reason we can use this softmax function because we can somehow consider the probability of an event or phenomenon to be realizing under some conditions. So we use the posterior probability function to say that to establish that the probability of X given M, a certain value of our response that will be equals to M, will take this shape, and we set that as a function. Okay. So now what I meant to do is to do the lab for the single layer. So yeah.
Oh, just getting ready to, discuss. No interruptions yet.
So the lab basically use this the ITER data set and set some testing and training set, and then does a couple of examples. So if I do a linear model, simple as that, with training, and then calculate the mean, minimum square error, this will be the value. While if I standardize and use, this is the case for this data set. If I standardize and use a GlimNet model with a cross-validation GlimNet, setting the measure as a mean absolute error, and only for the lambda, minimum lambda, because this cross, I suppose you know about those things, because this cross validation GlimNet thing means that when you are calculating the mean square error, this will be an adjustment of the mean square error, and you do this adjustment setting the lambda, choosing the lambda as its minimum value. So, and as you can see, the value is slightly different, so it's lower. So we can like make a comparison using a linear model, a GlimNet, and then using neural network. So you can use Kira and Torch within R. The book provides some indication for installation. Most probably you will be able to do that following these instructions. And then what Kira's, for example, the first example does is to set using these functions, Kira's model sequential, layer dense, layer dropout, and layer dense. This is the model, okay, that then we will fit. So these are a sequence of functions which are in this case setting an ReLU activation function, 50 units. You can set the units. It depends. You need to look at your data, have everything clear in your mind, where you want to go, what is the structure that you want to achieve, many things. So, and this is the model, then will be fitted and everything. Let's jump a second to Torch to see what they do. For Torch, you need to install these packages and then set the seeds, and then this is the model. So the model is a function of a function. You initialize hidden layers, you activate the ReLU, and then drop values following some threshold. and then you establish that it is not linear, the output that you want to achieve, and then again. So we can see this in this. Okay, there is a chat. I don't know. Yes, anyone to watch video? Okay, yeah. It's even in the notes later on. I'll push them. Okay, so this is the lab with torch. So I can use that and say that we have made this model. And so initialize the function and then forward the function. He says that basically the model has been defined by initializing and then forwarding the function and passing them to NN module. Okay, so this, I think it's good to have a bit of hands-on on these things. But then you can see that the model is set up with the matrix, and we can see the fit of the data here. And the torch tensor releases these values. This value, which is not the value that we are comparing in the previous two models. But we can see that we have the loss function and the mean absolute error here. And so this would be the first example with torch. Okay. I don't know if you have any questions, or maybe you've done it somehow. Yeah.
I don't have any questions. I it's nice to see it, nice to walk through it. I don't know if anyone else has thoughts. Okay, I guess let's go on.
Okay, just a little introduction to say that we have talked about single layers, but that's the foundation. So if we understand the single layers, then we can understand the multi-layer. So multi-layer is if first we had just one hidden layer, now we have more than one. So this AK function, we have two levels of this AK function. A sub K function. Sorry about that. And the second layer can be restricted because it's like when you use your predictors pass through some filters and then reduce themselves, then pass through another filter and then reduce themselves to finally find one value. Okay, so I didn't put much about that because it's the same exactly maths of this, same as before. Just the difference is that we have more than one layer, so we have more than one A sub K function. And then convolutional neural networks, particularly used for classifying images by recognizing specific features, distinguish each particular object class. The network first identifies low-level features in the input image. These features are then combined to form higher-level features. As I said before, after a single layer, the multi-layer, the convolutional layer, and all that is related with more modification of a single layer, it's quite the same, but they are adjustments. So here as well, it seems we are talking of the same thing, but it's not the same thing. It's slightly different. So we have convolutional filters. Convolution, it means you can imagine convolution like a multiplication of two factors. When you have two factors and you multiply these two factors, you obtain a result which is greater. So you have more choices. So you like convolution combinations. So the filters give you more opportunity for selection. So you have convolutional filters determine whether a local feature is present in the image. Then you have k different convolution filters in the first hidden layer. Typically, in the convolutional neural network, you use the Rayleigh activation function, and then you have the pooling layer. So you filter, and then you have a second layer of filtering, which is called pooling. So you pull out just the things that you think are more that your algorithm, that your structure believes to be the most suitable ones. And then you pulling them and put it on a side. So recurrent neural network is typically used in nature phenomenon, for example, because it's something that is recurrent. Not only that, but it's recurrent. So there is a sequence of facts that things that happen. So you have a sequence of predictors, you have a sequence of hidden layers, you have a sequence of probabilities that you extrapolate from your value. This instead of having your f of x function, which is the prediction for your y, which is the response, you have now this O sub L, sub capital L function, which is still the probability of your response. To minimize the residuals, you use the loss function, which is the difference between the observed value and the prediction made with probabilities, which is squared. So this is the structure for a sequential recurrent neural network, artificial neural network. And as you can see, this is a matrix, so you have more values. Then what else I've put here? Back propagation. So there is nothing here, but back propagation is basically a way to retrieve your parameters. So you basically execute the deep learning, and then you go back for finding your values, the values. Okay. Still in this nice, this is part 2. There is a nice explanation. So you need to basically go back to the gradient descent is differential equation made of differential equations. Okay, So you basically build up a matrix of differential equation results, and then you set up the value which are more the most the value that are the one that I use it for making the bells, which is minimize the distance of the residuals. And to do that, you start with the last values within the betas, and then you go back. You establish the last values, and then you go back retrieving the others. It's 10 minutes left, so I just say that you can eventually watch the video, or next week when we do the rest of the chapter, and I like to do the lab, we can see that again, talk about that again.
Okay. It's a good start. Like, it's always interesting. I don't know, interesting to walk through these things. So Jonathan, unfortunately, couldn't be here. He like works with Torch all the time. He's actively working on a model right now. Well, not right now, but he will be when he's back at work. It's interesting to me that this book came out, you know, just last summer, and they stop before Transformers, which is what is taking over deep learning. They don't talk about them at all. So I thought that was interesting. That's my main thought on this.
Yeah, maybe that would be interesting to do more examples. I've searched.
Yeah. I definitely plan to go through this lab. I started going through the lab and then like ran out of time to work on it, and have had 2 weeks in which I should have gone through the lab, and I didn't. So hopefully before next week, my plan is to do like one of the examples they stop and they could go a little further. And so I'm hoping to do that step. Anyway, we'll see how things go. So we'll continue next week.
Okay.
All right. See everybody then. Bye.
Thank you. Bye.
Thank you.